Hello everyone, welcome to my channel. I am Ehsan Ruhi, a lecturer in University of Massachusetts Amherst in Massachusetts. I am happy that today I will be speaking about my recent book published by Springer, the book called Advances in Direct Simulation Monte Carlo from Microscale to Rarefied Flow Phenomena. I wrote this book with my collaborator, Dr. Hassan Akhlaqi and Professor Stefan Stefanov. I work on rarefied gas since I started my PhD in 2006. So it is around very close to 20 years that I am working on rarefied gas and direct simulation Monte Carlo. So in this book, I discuss various topics around rarefied gas and micro nano flows. So in the preface, I speak about the detail and the chapters that were contained in this book. So there are around 10 chapters, as I told. In chapter 1, I start speaking about micro and nano flows or MEMS and NEMS, micro nano electromechanical systems. So what is the micro nano flow? What is the key feature of micro nano flows? What are the difference of micro nano flows with conventional flows? So in this short video, I try to introduce you chapter 1, which is Introduction to Micro and Nano Flows. So you see, in the very beginning of my book, I start with the length scale. So if we have a very large length scale, for example, distance between your home and your, let's say, your workplace, we use kilometers. And if we want to measure the height of one person, one child, we use meter, and then we go to centimeter, and then we go to millimeter, and if we further reduce the length, we go to the micro and nanometers. So these are the samples of micro and nanometers. So DNA, it is the DNA of a human, which is at the scale of nano. And coronavirus, we have also some years ago, the COVID problem, it was at the scale of also nanometers. And also micrometers are, for example, human hair. So it is a human hair, this human hairs that is magnified. It is at the scale of micrometers. And also the bacteria are at the scale of micrometers. So when we speak about flow at micro and nano scales, we assume we have a channel whose dimension are at the scale of or hair, or at the scale of a virus, a very small virus, nano scale virus, or DNA. So we consider flow through these geometries as small as a human hair, as small as a bacteria or virus. So what are the real application of these devices? So there are a lot of these examples that in the next pages I speak about them. Especially I want to move back to the hard disk drive, not the SSD hard disk drive. The previous generation of hard disk drive has a slider moving over a disk. The distance between this slider, assume it is a slider and this is the disk. The distance between the slider and the disk is at the scale of some 100 nanometers. So if you consider the disk here and the slider, the distance between the slider and the disk is, let's say, much smaller than human hair. It is the human hair over the slider of the disk. it is a dust particle over the disk, it is the fingerprint over the disk, it is a smoke particle over the disk, but the distance between the slider and the disk is much smaller than all of these, and it is at the scale of nanometer. So if we want to make our disk or a slider rotates faster over the disk, we need to know heat transfer and frictional force at this, let's say, convergent nano-channel. Okay, so this is the story of nano-channels. So where a nano-channel becomes more important. So with the advances of understanding of micro and nanofluidics and fluid mechanics at micro and nano scales, the people were able to make the distance between the disk smaller, the distance between the slider and disk smaller, and as a result, they were able to make more efficient disks. For example, Seagate were able to increase the capacity of the hard disk drive by changing the gas, the operating gas, from air to helium, and also the number of disks that can be put along each other. Also, there are other stuff that you can read in my book about them. In the next pages, I try to define some flow features. The fluid, or when considered as a molecular point of view rather than continuum point of view. So you know that air consists of a lot of molecules, but in traditional fluid mechanics, you consider that you consider control volume around the molecules and then consider a mass motion of the molecules. But when the scale is very small, you should consider the molecular nature of particles. So we introduced three concepts: the molecular diameter, intermolecular distance, and mean free path. Mean free path is the distance that is required between that is traveled by molecules between two successive collisions. And then I introduced different force mechanism between the molecule, or potential energy between the molecules. And as you see here in this graph, the Lennard-Jones model is the most common force model between the molecules. And in the next, I consider flow features at micro and nano scales. So the most important flow feature is that surface forces are more important than body forces at micro and nano scales, because the ratio of surface force to body force is proportional to 1 over length, and length scale is small at micro and nano geometries. So we will have much more surface force compared to body force, and we can ignore body force. So as a result, if you want to model flow at microgravity, for example at very high altitude in the space, you can consider microchannel and simulate your flow in a microchannel. So your microchannel behavior, the fluid behavior in microchannel is very similar to microgravity. And the other thing is that continuity assumption breaks down. So we cannot assume the flow is continuous. And also we introduce a new non-dimensional number called the Knudsen number, which is the ratio of mean free path of the gas to the characteristic length of the geometry. So mean free path of gas, of air molecules in your room, if you are at the standard atmosphere condition, is around 64 nanometers. So if your conduit or your channel has a characteristic length at the scale of nanometer or micrometer, these non-dimensional parameters becomes important. Or And I saw some example here. We plotted here the variation of the density and other parameters along the atmosphere, and then I introduced the concept of collision cylinder and drive the collision frequency and most probable molecular speed. And also we speak about the viscosity, what is the molecular relation for air viscosity. And we plotted some distribution functions here, and we find the relation between the Knudsen number and Mach number and Reynolds number. Then we classify the flow according to the Knudsen number. If the Knudsen number is very, very small, smaller than 0.001, the flow is continuum. As the Knudsen number increases, the flow enters the sleep regime, transitional regime, and free molecular regime. So, and each regime, the flow field requires a specific treatment. So, we define the gradient length parameter. Sometimes the geometry is not small, but the variation of the parameter, for example, the gradient of the density, the gradient of pressure, gradient of temperature, gradient of the velocity, if they come at the denominator and the parameters become at the numerator, this ratio gives us a length. This length can be let's say can be very, very small, and it means that at the variation of the parameters occurs at the length scale compared to the mean free path of the molecule. So the real Knudsen number is the mean free path divided by gradient length scale. So for example, for a flow, hypersonic flow around the cylinder, if we plot the variable length scale, you see that in the shock wave that is formed in front of the cylinder and in the wake formed behind the cylinder, this gradient-based Knudsen number is very large. So the conventional approach, such as Navier-Stokes equation, are not valid at this region, at the shock wave and at the wake behind the cylinder. Okay, so we do some examples here and also some more examples. Okay, and then at the end of this chapter, I introduce some peculiar physical phenomena of micro and nano gas flows. The first interesting phenomena is cold to hot transfer. You know from heat transfer that fluid flow moves from hot to cold. The energy moves from hot to cold direction. Okay, it is the Fourier laws. But at the micro and nano scale, we can observe that energy moves from cold to hot. So you see here at this, it is a cavity geometry. This is a very low Knudsen number. At the top, it is the Navier-Stokes. Bottom is a molecular simulation of the flow. At the very low Knudsen, they are very close. As the Knudsen number increases, the Navier-Stokes solution becomes 1 compared to the molecular solution, because the continuum assumption fails when the flow is rarefied. And you see here, these are the lines are heat line. The lines move from blue, which is cold, toward the red, which is hot region. There are some physical reasons that I will describe this in next chapters of the book. That the flow, why the flow moves from cold to hot region. So it is also the plot of the cold. You see the heat lines move from the cold region toward the hot region. That is simulated by, on the right, it is by direct simulation Monte Carlo, which is a molecular approach. On the left, it is simulated by R13, regularized 13 moment, which are more accurate than Navier-Stokes equation. And it is also a step geometry. So not only in cavity geometry, but also in a step geometry, we observe cold to hot heat transfer. The other thing is the Knudsen paradox. If we plot mass flow rate or mass flux, normalized mass flow rate in a microchannel, we observe that the minimum mass flow rate occurs around Knudsen 1, and after Knudsen 1, the mass flow rate starts increasing. So the minimum mass flow rate in a channel occurs around Knudsen 1. And we discussed why this happened, why this phenomena happened. The other thing is nonlinear pressure distribution in a microchannel. If you solve a microchannel in incompressible flow assumption, you observe the pressure in a microchannel drops linearly. But when we have the rarefied flow, which is also compressible, the compressibility gives some, let's say, some slope to the pressure distribution, and the increase of the Knudsen number result in less curvature in the pressure in the microchannel. We also plot the Poiseuille number. Poiseuille number is the ratio of CF of the multiplied by Reynolds by the Poiseuille at the continuum limit. So the Poiseuille number is the Poiseuille number at the rarefied regime is different from Poiseuille number at the continuum regime. The other thing is the thermal polarization around the constant temperature sphere. Even though you have a constant temperature sphere, in a rarefied gas you can see temperature distribution. So you start a flow at the same temperature with the sphere, but you see temperature distribution. So in the rarefied regime, when the flow is not continuum, the velocity field and temperature field are highly connected. So you see, in a few pages ago, I show you the heat transfer from cold region to hot region. This is due to second gradient of velocity. So velocity results in heat transfer from cold region to hot region. On the other side, here the velocity field results in temperature non-homogeneity in a channel. At the end of this chapter, we have some references, and then we go to the chapter 2. So it is a very good summary of the peculiar flow of the micro nanoscales, and also what is the micro nanoscale and micro nanochannel really means. Okay, I will continue these videos from our book with the next 9 chapters, and I will be happy if you liked this video and you are interested that these types of video continues. Like my video, share the video link with your friend, and also let's say put a comment and write me what topic you are interested that I prepare videos. So, and I would like to add that the next edition of this book will include machine learning, and hopefully will be published in 2026. Thank you for watching my video, and see you in my next recording.